evening to all of you. I am Dr. Ritish Kumar. I'm going to present the lecture on the topic of microstrip line, which lies in the subject of microwave and radar engineering. So this is my first lecture. Microstrip line is nothing but transmission media through which information exchange takes place from source to load. But it is a kind of planar strip line. That's why we call it is a micro strip line. So we will begin the topic, the transmission line. So based on the construction point of view, we can categorize the transmission media or transmission line in two forms. The first one is geometrical, and the second form is the mode form. So in the geometrical form, we can categorize the transmission line based on the single conductor or multi-conductor. So as you can see in the figure here, this is a cross-sectional view of the coaxial cable. As you all are aware about the coaxial cable, so it has inner conductor, then outer conductor. In between these two conductors, there is some dielectric media, that is Teflon. So here we can say this transmission line having the two conductors, the inner conductor and outer conductors. So we can say it has more than one conductor. While in the case of waveguide, this is a kind of waveguide. So this transmission media is totally made by a single conductor, as you can see here. So this is a difference between coaxial cable and the waveguide when we correlate the things in the point of construction point of view. But apart from this, we can categorize the transmission line based on the mode point of view. So in mode point of view, we have a kind of TEM mode and non-TEM mode. So what is a TEM mode? TEM stands for transverse electric magnetic mode, while non-TEM modes, so we have different kinds of non-TEM modes. The first one is TE mode, TM mode, then HEM mode. So TE stands for transverse electric field, TM stands for transverse magnetic field, and HEM stands for hybrid electric magnetic mode, right? So based on the multi-conductor transmission line, we have different kinds of media. So such one is the coaxial cable, twisted line, and parallel plate line, etc. While based on the single conductor, we have the transmission line is a waveguide. While in the further slides, we will discuss about the topic of TE. What is the TE mode? What is the TM mode? What is HEM mode? So in broad sense, we have a transmission media like. So what is the TEM mode? TE stands for transverse electric magnetic mode. In terms of electric field and magnetic field, we can say if the wave propagate in the direction of, suppose we have a three-dimensional coordinate system x, y, z. This one x, y, z. If I say the propagation is along the direction of z, then we can say for the TEM mode, the condition must have Ez should always be equal to 0, and Hz should always be equal to 0. That is the condition for transverse electric magnetic mode. In other words, we can say it has the electric field and magnetic field both has the transverse nature of the direction. If I say the propagation direction in the z direction, while in the case of what is the condition of TEM mode? TEM mode supports what kind of transmission line supports the TEM mode? So there should be two conditions. The first one, there should be at least two disjoint conductors, and the second condition, medium filling the cross section is homogeneous, isotropic, and lossless. So if you see this coaxial cable, if I say, so the first condition says there should at least two disjoint conductor conductors. So in the case of coaxial cable, you can see there at least two conductors are present, uh, and both are the disjoint conductors as well. While the second condition says the medium filling the cross section is homogeneous, isotropic, and lossless. So in the case of coaxial cable, these two conductors separated by a Teflon material. So we can say this inner conductor filled by the homogeneous medium, that is Teflon medium. So the second condition also verified. So we can say coaxial cable has a pure TEM mode, uh, in further side we can see the waveguide will have the TEM mode or non-TEM mode. So TEM mode, transverse electromagnetic mode. So here you can see the transverse nature of electric field will be exist in the case of transmission line if the propagation direction, if I say in the z direction. So the condition always be the Ez should always be equal to 0, while Hz should not equal to be 0. That is the condition of transverse electric magnetic mode, mode. While if I say the transverse magnetic mode, that is the it has the complementary nature of the TEM mode. Whatever we have in the TE mode, just we can complement of it. So we can say if the propagation, the wave propagation in the z direction, we have the electric field Ez should not be equal to 0, while Hz should be equal to 0. You can see this is a complementary nature of TE mode. If I say hybrid mode, so in hybrid mode you can say Ez is not equal to 0, while Hz should also be not equal to 0. That should be the condition for hybrid mode. We can say this mode is also HEM mode, hybrid electric magnetic mode, right? So this is the condition for the TE mode, TM mode, and hybrid electric magnetic mode. So actually our topic of this lecture is microstrip line. So we will move towards the microstrip line. So this is a kind of planar transmission line. It has a small size, and it has the capability to compatible with the IC technology as well. So here the construction point of view, we can see the strip line and microstrip line as well. So you can clearly see here the strip line has the two disjoint conductor, right? Here the two disjoint conductor here present, while in the case of microstrip line also two disjoint conductors are present. But in the construction point of view, you can see this strip, it has the strip width is W, while the same we have in the case of strip line. But you can see the inner conductor has the surrounding media is homogeneous, while in the case of microstrip line you can see the above the surrounding medium is there, while below the microstrip line the surrounding medium is some kind of material that has the electrical permittivity epsilon r. So we can say in the case of microstrip line, microstrip line has two media. The first one is the air media, while the second one is the material, the dielectric material, which has the electrical permittivity is epsilon r. While in the case of strip line, only the surrounding area is homogeneous. So we can say in the previous slide we have seen the condition to have the pure TEM mode. There should be at least two disjoint conductor present in the transmission line, while along with the cross section medium should be filled by homogeneous medium. So these two conditions are verified in the case of microstrip line. So we can say strip line. So we can say strip line has the pure TEM mode, while In the case of microstrip line, you can see the strip line lies in between two mediums. So we can say it has not contained the pure TEM mode, but it contain the quasi TEM mode. We can say quasi TEM mode. Why? Because it has two media, right? The first one is the air and second one is the dielectric material. It could be any material such as Teflon, such as FR4, we can say FR4 and Teflon as well, we can say. So in the if I say the electric field distribution of the strip line and the microstrip line, here you can see if I treat this strip line, this conductor has a plus polarity and this one is having the negative polarity. So electric field moves towards the plus to minus direction. So it has the electric field has a direction from positive to negative, while the magnetic field has the direction surrounding the electric field. In the case of microstrip, you can see the electric field comes from plus to negative. All the electric field comes from positive to negative. So some of the fields lie in the free space. You can see air, media, and this field is known as fringing field. Fringing field. So this due to this fringing field, it has some limitations. So this is the main electric field distribution difference between the strip line and microstrip line, in broad sense we can say the strip line has the TEM mode and microstrip line has the quasi TEM mode. This is the important term that you need to remember, right? So this is a kind, why we call this is a planar transmission line. So because if I look from the top of this strip line, we can able to see it is a kind of surface. So it has lie in the XY plane. That's why we call this is a planar transmission line as well. So next, in terms of phase velocity, so it has two media. The microstrip line has two media. This is a dielectric media, as I told you earlier, and this is a air media. So this is dielectric medium. So phase velocity in both medias are different. So due to which properties of this microstrip line will differ from the properties of strip line as well. So this is a main point. As you can see, as I discussed already, quasi TEM mode is a dominant mode of the operation of most of the planar transmission lines. Not when the strip is completely enclosed, as in the strip line, as I discussed already in the previous slide as well. So here we have the phase velocity BP1, and in this medium BP2. So BP1 is totally different from BP2. Suppose somebody asks you to design a microstrip line for a 50 ohm impedance. So how we can proceed to design a microstrip line? So there is a processor to design a microstrip line. So you can see here, this is a effective dielectric formula for the microstrip line here. So you can clearly see here. So this first part is nothing but the average of two medium. If I say the dielectric permittivity means permittivity, relative permittivity of air is equal to 1, and the dielectric media has a relative permittivity epsilon r. So this is nothing but the average of two medium permittivity as well, and this is the extra part. It has a very less value, so we can approximate it. This effective dielectric constant is approximately equal to the average of air and material permittivity, right? So it always lie in between the 1 to epsilon r. So if you see the total formula here, so we can say the effective permittivity is totally depend on the relative permittivity of the material, while for the construction point of view, we have the d w by d ratio. So this is a w by d ratio, or we can say w by d or d by w ratio, you can say. So what is the d and w? So in the picture you can clearly see here, this is the d, that is the dielectric thickness of the media, and w is the width of the strip line. So effective relative permittivity depends on the two parameter, that is w or d, or we can say w by d ratio. So you can clearly see here, if w by d ratio increases, higher w by d ratio, lesser will be the fringing field. Why? Because if you relative permittivity will become high. Due to this high relative permittivity, most of the electric field comes down in the dielectric media. That's why we can say, if you increase the w by d ratio, we will have a higher fringing field. So this is the how to find the effective relative permittivity. So these are the formula that you need to take to design a microstrip line. So this is a microstrip line. In this we have two parameters, w and d, and if you want to design a microstrip line for a certain impedance, that is Z0, then we have a formula for this. Z0 equal to for w by d is less than equal to 1 and w by d is greater than equal to 1. For these two cases we have a different two formulas. So you can see, for w by d is less than equal to 2, right? Here you need to apply this formula, and for w by d is greater than 2, you need to apply this formula. Here the constant a and b we can have. This is a formula, this is a b formula. So these formulas you need to remember to design a microstrip line. So if you have a question such, for an example, using a substrate of dielectric constant 4, this is epsilon r is equal to 4. This is a thickness, that is thickness of the substrate, that is d is equal to 1.6 mm. Design a 50 ohm microstrip transmission line with w by d is greater than 2. So you can have these formula, and for w by d is greater than 2, you have to apply this formula for to get the w by d ratio. So you can see, you have to apply this formula. So in the picture you can see, so in this you will see here only the b comes into the picture, right? So you have to apply the b formula here. So you already know your desired impedance, that is 50 ohm. You need to apply Z0 equal to 50 ohm, right? So after applying, and epsilon r you already know 4. So if you apply these value in this formula, then you will get b is equal to 5.92, right? After putting this b into this formula, then you will get w by d is equal to 2.92. So you know the thickness of the substrate, that is 1.6. So you know the value of w by d. So after putting the value of d, you will get the width of the transmission line, that is this one. So you can clearly see here, w by d is inversely proportional to the if you increase the width of this transmission line, you will have the low value of characteristic impedance Z0. So this is an example for designing of a microstrip line. Now, the another important parameter, that is surface wave loss. What is the surface wave loss? As we clearly see here, this is a, it has two media. So this is a discontinuity we have in uh, two medium, air and dielectric permittivity epsilon, or we can say substrate. So this is the interface between these two media. So at the interface we will have some kind of surface wave loss due to the having due to having the different phase velocity, right? So in terms of cutoff frequency, means at certain cutoff frequency, more than this cutoff frequency, we will have a surface wave mode as well in the microstrip line. So this is a formula for cutoff frequency of surface wave mode, right? After you can clearly see here, if you increase the d, you will get fc will become less. So if you want to increase the cutoff frequency of surface wave mode, or if you yeah, so for to decrease the surface wave mode, you will have the you will need to take the d is less than as far as possible, right? So our requirement to have fc as high as possible in the microstrip line, right? So to have the surface, to minimize the surface wave loss in the microstrip line, this is our requirement, right? So as per the requirement, you have, if you decrease the, if you increase the width, then you will get, if you decrease the width of this substrate, you will have the higher cutoff frequency. So this is the another drawback of the microstrip line, that is surface wave loss. So at last, for the microstrip line, we have a kind of surface wave loss, as I discussed already, and the second one is the radiation loss as well. So to reduce the radiation loss, as we can see, we need to take high epsilon r for the substrate and thin substrate as well. And to reduce the surface wave loss, we need to take low substrate permittivity and thin substrate as well, as I discussed in the previous slide. So this is the mode symmetry we have in the case of microstrip line. So this is a kind of even mode symmetry. You can see this is the field distribution of the transmission microstrip line. If you see, this is a mirror image of the field distribution as well. That's why we call this is a even symmetry of the field distribution. That's why we call this is a even mode. So here you can see, if you look, this is a kind of odd symmetry. If I say this is not a kind of mirror image of these two field distribution, that's why it is a kind of 180-degree phase shift. That's why we call this is a kind of odd mode of a microstrip line, right? So I hope this term is clear to all of you. What is the even mode, what is the odd mode? Even mode should have the symmetry about this axis, and odd mode will have this asymmetry about this axis. So this is a kind of even mode and odd mode of the microstrip line. This is a variation of effective dielectric constant versus frequency. As you can see, as you increase the frequency, as you move towards a higher frequency, so the effective permittivity will become equal to the relative permittivity of the medium. As you can see, for the 10.2, at this, below this frequency, it has variation from effective relative permittivity to relative permittivity of the medium. So as you increase the frequency, you will have the effective relative permittivity becomes equal to the relative permittivity of the medium, right? So this is the variation of effective relative permittivity versus frequency. So I hope these topics of microstrip plan is clear to all of you. So in next lecture we will discuss some other topics as well. Thank you to all.